We are building the future on a 1940s bottleneck. Every modern computing workload, from unpredictable network traffic to generative AI, is fluid and highly uncertain. Yet, at the hardware level, we force all of that nuance through rigid, one-dimensional logic gates that can only snap between 0 and 1. We try to compensate for this physical limitation with software workarounds. We stack massive probabilistic layers, like standard AI routing and complex operating system heuristics, on top of this binary foundation. But calculating probabilities using absolute Booleans requires staggering amounts of raw processing power. The industry's proposed solution is physical quantum computing, but fault-tolerant, cryogenic quantum mainframes are decades away from sitting on your desk, and they offer zero immediate value for edge devices or personal computing. The QxBin framework presents a different approach. We don't need to wait for new silicon. We can bypass the physical hardware barrier entirely by changing the mathematical language we use to talk to the classical CPU. Software-based probabilistic compute provides a method to bridge this gap using current systems engineering, making advanced logic accessible on existing hardware. Think of true uncertainty as a spinning coin. While it spins, it isn't heads or tails. It is a continuous, uncollapsed probability state. Classical computing cannot represent a spinning coin. A deterministic bit must immediately choose a side before the processor can run the next instruction. QxBin solves this by replacing absolute binary values with a mathematical substitution. Instead of storing a definitive 0 or 1, we encode the data using fractional exponents to represent the probability of each outcome. This mathematical shift means a standard classical processor can hold, process, and evolve multiple overlapping probabilistic states concurrently without forcing an immediate decision. We are mathematically emulating quantum superposition. This democratizes advanced, quantum-inspired logic, bringing it out of massive corporate labs and directly onto any standard developer machine. This diagram shows the specific equation replacing the standard binary bit. QxBin calculates state using the formula bias to the power of n divided by 1 minus bias to the power of m. When we ingest uncertain data, we set a baseline numerical bias. As the input variables change, this base value shifts dynamically to reflect the raw incoming probability. The real mechanics are driven by the n and m exponents. As the bias moves, these two exponents react, exponentially skewing the final calculated value toward either 0 or 1. We call these exponential weights directed contributions. The vector lines here show the pull of probability, mapping exactly how strongly the data leans toward a specific outcome at any given moment. By carefully balancing these opposing directed contributions, the algorithm mathematically suspends the data. It maintains a precise record of competing probabilities, mirroring how physical qubits maintain superposition. Because this is entirely math-based, these complex fractional states execute natively and seamlessly on standard deterministic floating-point hardware. These formulas are our new atomic building blocks. We have replaced the rigid physical state of a transistor with a fluid, continuously evolving mathematical state. A single fractional equation is useful, but real workloads require complex structure. So we expand that single point outward into a two-dimensional spatial grid called the Binary Probability Matrix, or BPM. Mapping uncertain data across a 2D spatial grid gives us multi-dimensional context. A flat one-dimensional bit array loses the relationship between complex variables, but a matrix preserves the entire topology of the data. As new probabilistic logic feeds into the edge of the matrix, we trigger chain evolution. The incoming data causes the grid cells to ripple, continuously recalculating their fractional weights without ever committing strictly to an off or on state. Throughout the entire intermediate processing phase, the matrix remains fluid. The system evaluates thousands of cascading probability shifts simultaneously. Eventually, the system needs to make a definitive decision. This requires a probabilistic measurement phase, which we refer to as the collapse. We trigger the measurement, and a sweeping function passes horizontally across the matrix. It instantly locks the fluid pulsing probabilities into rigid, high-contrast zeros and ones. Forcing this final deterministic output is structurally necessary. It translates the nuanced probability back into the flat binary that standard CPUs and external APIs require to execute an action. The BPM architecture provides a distinct advantage. It allows the system to think in complex, fluid probabilities, but ultimately act in strict binary. To make this practical, QxBin deploys across 3 distinct classical tiers. We start at the lowest level, Tier 1, running native C code directly on the edge. This zero-dependency C implementation is lean. It allows single CPU cores and embedded devices, like localized pick-stop kiosks, to run personal probabilistic simulations with minimal overhead. For heavier workloads, we scale up to Tier 2, the cloud. This tier uses an OpenMP pipeline to route data streams across multiple CPU cores simultaneously. Parallel CPU execution handles massive ensembles of qubit chains exponentially faster than a single edge device, allowing for rapid batch processing and continuous feedback loops. However, the ultimate scaling substrate for processing multidimensional mathematical grids is the GPU. Traditional linear Boolean code creates massive bottlenecks on graphics cards, but the spatial grid of a binary probability matrix maps perfectly to NVIDIA's highly parallel CUDA architecture. This brings us to Tier 3, the dedicated GPU acceleration repository, QxBin CUDA, version 1.1. The stack is built on 3 distinct structural layers. The high-level CUPI layer allows for rapid prototyping and visualization, while the Python bindings provide a bridge for developers to execute complex logic from a standard Python environment. Beneath that sits the native CUDA C++ kernel. This layer strips away the overhead entirely, delivering maximum speed for custom integrations and high-performance production workloads. This GPU layer hits a very specific benchmark, simulating ensembles of over 1,024 fractional qubits at interactive room temperature speeds. Classical hardware isn't the true bottleneck preventing probabilistic computing. A highly optimized, mathematically aligned C and CUDA architecture proves that the compute power is already here. We can push this math further down the stack, moving from raw architectural benchmarks into high-level operating system integration. At the kernel level, operating systems rely on rigid legacy heuristics, like the Linux completely fair scheduler. By injecting probability matrices directly into the OS, we replace those static rules with dynamic evolution. This enables uncertainty-aware memory management and adaptive power decisions. The kernel learns to anticipate bursty, unpredictable workloads based on real access patterns rather than flat if-then statements. We can apply this exact same probabilistic logic to artificial intelligence, specifically upgrading open-weight models like Grok 1. This is the objective of the QxGrok implementation. We take the evolving matrix logic and embed it into the neural network's routing layer. By replacing standard deterministic routing with a probabilistic system to resolve nuance and ambiguity with higher precision than rigid token prediction. QxBin functions as a foundational replacement for the classical compute substrate, scaling from kernel-level scheduling to high-level AI routing. Deploying a new computing substrate requires widespread adoption, which is driven by the QxBin ecosystem's open accessibility strategy. This image outlines the custom MIT license structure. The framework is entirely free for testing, experimentation, internal organizational use, and building software on edge devices using your own development resources. When an organization scales this logic to create and sell a commercial tool or API, a 51% revenue share trigger applies. This aligns incentives, ensuring the creators pushing the frontier receive the sustained support needed to fund long-term ecosystem development. This structure supports Rupesh Malpani and pikk.company's core mission, democratizing quantum-inspired logic so any individual can experiment with advanced computing outside of massive centralized corporate labs. Advancing our compute capabilities doesn't require waiting for cryogenic mainframes. It requires changing the mathematical language on the devices we already own.